All right, in this video, we are jumping over into chapter 12. This is going to be a shortened version of the chapter 12 introduction, but hopefully it kind of gives you an idea of where we're headed with the rest of this chapter, where we're headed in multivariable calculus even. So chapter 12 is going to be about vector functions, and we have already dealt with vector functions a little bit, okay, in the simplest form as a line in space. Okay, a line in the three-dimensional field can be represented as a vector. It's the vector form of a line, right? So we represented it as r naught plus tv. And we kind of separated that out into x, y, and z components by saying that this was maybe like x naught plus direction number at, y naught plus bt, and z naught plus z. So that was our first ever vector function. It was a function of time. We want to do things more complicated than that. We would like to do some kind of curve in space. So we can extend this kind of definition to be a space curve, okay, where we have a vector equation, but we can define it as a set of parametric equations, just like we did with a line. X equals f of t, y equals g of t, another function, z equals another function of t. And f, g, and h are continuous functions on an interval, okay? And that's important. Now that we have some kind of function, let's say like we're given here in this example, okay, we still have all the same things we would have when we dealt with functions in 2 dimensions. So we have domain, we have range, we have continuity, we have limits, and as we're going to get to in this chapter, we also have all of the calculus items, integrals, derivatives, that kind of thing. Okay, what I do want to draw your attention to is how is this curve drawn out? And these 2 pictures are trying to illustrate here to you that the curve we're looking at is this, and this is all we would see in space. And notice it has directional arrows because this is parameterized in terms of time. It definitely starts at a certain place and then ends at another place. But we can think about this curve being created as if there was consistently some vector coming out of the origin and pointing at a point on the curve. And if we just had, again, like infinite vectors in here for every single moment of time, right? All of those, the tip of all of those vectors would be the curve traced out in space. Okay, so we're kind of using, again, that understanding that a vector could also identify the location of a point to kind of illustrate this out. So remember, okay, we have a domain, but I want to make sure we've kind of thought about this because our domain, our input is t. So our domain now is some subset of the real numbers, right? There's some, maybe it's all real numbers, but maybe it's not, depending on what our functions are, but our input is t. Okay, some input of t. But our range, what we're getting out, okay, since we're creating a whole line, okay, is a set of vectors. And by a line, I mean a curve. I want to be more specific about that. Set of vectors. Okay, so input 1-dimensional, output multiple dimensions. And that'll be different than what we encounter starting in chapter 13, where we do have an input of 2 or 3 dimensions and an output of 2 or 3 dimensions. But right now, okay, input 1 dimension. We're inputting everything in terms of time, and our output will be a set of vectors displaying points in space. Okay, so an example of this would be if I substituted t equals 0, part of my domain, into this vector function I highlighted, my result would be the vector 0 minus 1. Why does it do that? 0 minus 1. 2 sine of 0, and sine of 0 is 0, so 0. And then negative natural log of 2. Okay, so the output is a vector pointing at the tip of that vector being the point in space we're referring to. Okay, and don't forget, you can always, as this reminds you, write vector functions as a linear combination of the standard basis I, j, and k. Okay, so we can either write it in the vector form that I showed up here, or you can write it as this equation did here in ijk. Okay, so that's how we define a space curve, quote unquote, a vector function. So now let's do all the calculus with it. Let's start at the very beginning, just like we did in BC. Okay, the limit of a function, a vector function, is a vector. Okay, so instead of it being, because our output is our vectors, okay, our range is a set of vectors, the limit as our input in the domain approaches a certain value will be a whole vector. Okay, and you can actually evaluate it. The nice thing is, to evaluate the limit of a whole vector function, you just apply the limit to each component separately and see where it takes you. Now, this is important provided the limit exists. So if one of those parts doesn't exist, then we say that the whole thing doesn't exist. Also, the domain of the vector function is the intersection of the domains of each component. So remember, when you were writing domains in all of algebra and you wanted to do multiple intervals, sometimes you would use a union symbol, which meant like this and this. I do not want a tiny parabola. I want a union. Now we're going to use the intersection. That's an upside down, kind of like an N for intersection. That means we're going to have to look at where the domains overlap. So for example, here, let's take a limit and domain. So the limit as t approaches 1 of this vector function, 3t minus t squared, okay, will be the limit as t approaches 1 of 3t, and the limit as t approaches 1 of negative t squared. E. Okay, so easy limit, nothing difficult happening on here, but 3, negative 1. Okay, limit of a vector is a vector. Notice I used my pointy brackets, my vector notation. Okay, well, what about the domain? Okay, also pretty simple. What is the domain of 3t? Okay, all real numbers. What is the domain of negative t squared? Also, all real numbers. So the intersection of real numbers and real numbers, where do those two sets overlap? Well, it's everything. They have everything in common. The domain of the vector function we just gave is all real numbers. Okay. If we had something where it didn't, like we'll do some examples in class where we'll have to actually write a combined domain. There will be discontinuities. We'll have to decide, or I guess combine the restrictions to write a new domain. But I do want to talk about continuity. And hold on real quick. There we go. A vector function is continuous at a certain point, okay, if the limit exists and the function value exists. That should sound very familiar because this is our 1, 2, 3 definition of continuity. Okay, 1, does the value of the function exist at A? Let me not write equals. Let me write exists. You should be specific. You should write what it equals. 2, does the limit as t approaches A of r of t, does that exist? So limit from the left and right. We'll talk about left and right and why it works right now, but why left and right, quote unquote, will not work in chapter 13. 3, that value r of A should be equal to the limit as t approaches A of r of t. Okay, should be equal. That's our definition of continuity from BC Calculus. And again, a vector is continuous on the interval if it's continuous at every point, meaning you can't exclude anything. So, for example, if we were to discuss the continuity, that means where is this function continuous? Okay, it will be continuous on the domain. So just where it is exclude the discontinuities, I guess is what we're trying to say here. Okay, so what are our domains? So for the first component, okay, for the x component, I have to have that t is greater than or equal to 0. For the second component, I have to have that t is specifically greater than -1. And it can't be equal to 0, or it can't be greater than or equal to -1 because it's in the denominator, and we don't want to divide anything by 0. Okay, and then for the last one, there's no square root, so I really just need t to not be plus or minus 3. Okay, so we need to combine. So this is a good example of us combining these restrictions to make a domain. So r of t will be continuous on, okay, well, it has to be greater than or equal to -1, or excuse me, it has to be greater than -1, but it also has to be greater than or equal to 0. So if this is a restriction, this overpowers anything less than that. Okay, so really, this restriction is included in these restrictions. So we're going to start at 0 and go up to 3, okay, and then skip over 3 and go to infinity. So also, we didn't have to worry about -3 because this restriction took care of the fact that we can't have any negative t values. That's what it means to find the intersection of the domains. And if you really wanted to write it out as a bunch of intervals and then see where those intervals overlapped, the first interval you would write would be from 0 to infinity. The next interval for the y component would have been from -1 to infinity. And for the last one, you would have had to write -infinity to -3, union -3 to 3, union 3 to infinity. So we're looking for where all three of these things have common ground. Where do they all exist? Well, we can't include anything negative, so that ruled out this part, and that ruled out some of this part, and some of this part. Okay, so do you see how we ended up using this part of this, and part of this as our intersection, what they all had in common? Okay, what is one more thing, okay, that we want to talk about is that these space curves lie on the surface of three-dimensional objects. And that's what chapter 13 is about, is actually describing these three-dimensional objects. Okay, well, how do we describe those surfaces? Right now, we're just describing a curve in space, like you would take a piece of string and kind of like waved it in the air or something, or wrapped it around something. But in chapter 13, we'll start talking about what is the structures that curve is being kind of wrapped around. But we want to talk about some of the more common curves, and that is, one of them is a helix. Okay, so let me actually draw it. It's kind of a bad diagram here, but the helix starts here from t equals 0 and wraps around this cylinder like this. Okay, so it goes around that way, goes behind the cylinder on that side, and then wraps back around this way. It has the vector equation, r of t equals cosine of t, sine of t, t. So I want you to think about, if you didn't know what it looked like, you could always plug in values of t and kind of graph it a little bit. You get to choose the values of t that you want to plug in, so highly recommend plugging in values on the unit circle here for t. But what I want you to notice is if we did not have, let's say for instance, we just didn't have this part, okay, that is a circle, okay, cosine and sine, that's the unit circle, right? So that would be just a graph going around in the xy plane over and over and over again. But because we have this t component, we're also getting some height, okay? As we're going around the circle, our z value is also changing as t changes. So that's what gives us kind of this vertical, oh, that was a really bad line. Sorry, everyone. This vertical rise, okay, is this extra t component here. Okay, and if we wanted to look at kind of what that surface is, and this is what we'll get to later, we could kind of try to combine it into something that looks like x squared, y squared, and then using x, y, and z instead of, and kind of eliminating that parameter t. So I want to look at another one. Okay, I'm going to actually use a different technique, and this is called looking at different like slices or traces of the curve. And so we're going to compare, knowing that if I separated this out into parametric form, I could write it as x equals t, y equals t, z equals t squared. Okay, so if I look at the, let's say, if I was looking straight down at this function from above, okay, looking down at the xy plane, what would it look like? Well, I would expect to see a line. The relationship between x and y is that they're equal. Y equals x. So if I looked down on this function, I should expect to see a line. Maybe I don't know if I can expect to see some depth or not, but at least like the trace looking down, okay, would look like y equals x. Okay, well, what if I looked at the other planes? Okay, what if I looked at, let's say, the xz plane? Okay, so the xz plane. In this case, z is equal to x squared. Okay, so if I looked at the xz plane, I would expect to see a parabola like this. Okay, and then the same thing happens if I looked at the yz plane. Okay, I would also see that I'm getting, actually, yeah, it's fine. Z equals y squared. Okay, just by showing the comparison between t and t squared. So if I'm thinking about this, if I look at the xz plane, I see a parabola. If I look at the yz plane, I see another parabola. Okay, that means if I was looking at it from the xy, like the xy plane served as my kind of my eye level, I would be seeing a whole lot of parabolas. Okay, so this is again something I want you to end up playing with. I'm going to post in the comments for this video, I'm going to post the link to GeoGebra so that you can kind of play with this on your own. But what this is doing, and let's see if I can draw us, this is a 3-dimensional graph paper happening right now. Okay, X, Y, Z. Okay, in the XZ plane, you're seeing some kind of parabola like this. I'll do the YZ plane in a different color. In the YZ plane, you're also seeing a parabola like this. So really, this shape that we're seeing is lying on a paraboloid, this kind of spinny top looking thing. Okay, but where does the actual curve lie? Okay, so that answered what surface it lays on. It lays on a paraboloid. The curve actually lies on this trace, y equals x. So let me pick a different color here. That would be the equation y equals x. So it, like this one right, oh, that was bad. Here. And then in the back, it would go out this way. Okay, I will compile a better 3-dimensional picture for you. I'll add it to this video in a second. Okay, so let's let the computer do what I cannot, and that is be way better at producing graphs. You know, my drawings are adequate at best. So what I've done is I created the surface that this curve we were talking about is lying on. And so there you have it. You can see that it is a parabola. So when I looked at here is the It's hard to get it straight on, but here's the YZ plane. Okay, you can see that it would give the shape of a parabola. Okay, here is the XZ plane, again, showing the shape of a parabola. Okay, and then when I look down on the XZ plane from directly above, you can see that line y equals x right there in the middle. Okay, and it's this curve, the space curve, the black dotted line there, okay, lies on the surface of this three-dimensional object. And I've written the equation for it over here, but we will learn, I think you can kind of see how we got that, or how I created that, kind of just making a relationship between x, y, and z. But we'll talk more about the general form for a paraboloid and all that stuff in chapter 13. I'm more focused on you being able to tell me that this curve is a parabola, and that's kind of just what it looks like. Am I focused on you drawing it? Absolutely not. But I wanted to show you kind of how I applied those, taking a slice, okay, comparing 2 out of the 3 variables, how that helped me kind of picture what this curve looks like and what surface it might be lying on. We'll definitely do some more exploration on this in class.